good afternoon, good evening, depending on wherever you are. Good day to all of you. Ladies and gentlemen, I'm Shivani Khare, your host for the day. I take great pleasure in inviting all of you to the Global Emerging Tech Summit 2021, organized by University of Emerging Technologies, co-sponsored by the Emerging Tech Foundation, Computer Society of India, Global Engineering Deans Council, and International Federation of Engineering Education Societies. University of Emerging Technologies is about E5, evangelize, educate, empower, enlighten, and engage about emerging technologies. This conference is about bringing emerging tech closer to the next generation of professionals and making effective use of virtual education. We are delivering a series of 6 lectures ranging across various topics in emerging tech over 3 weekends, that is 6 days, Saturday and Sunday in 6 sessions. Every session is opened by a keynote speaker who is an eminent personality from either tech or education, followed by the lecture of the day. The attendees are encouraged to send in their questions during the lecture. It can be via chat, tweet, email, and then we'll have a separate Q&A session soon after the completion of the lecture. After that, Mr. Prasad Mahbudari, CEO of University of Emerging Technologies, will deliver his closing remarks and also answer some of your questions. Now I take pleasure in introducing a keynote speaker for the day, Mr. Venkatesh Parasuram. He is the Vice President of Computer Society of India. Mr. Parasuram is a postgraduate in management and a serial entrepreneur. He carries 25 years of work experience in a wide range of domains. Currently, he is dedicating his time and energy to the Computer Society of India for empowering the student and teaching community with his collective learning skills and upgrading the knowledge to meet the industry expectations. He is also supporting various organizations in the product and process development as a technical advisor. Please welcome a keynote speaker for the day, Mr. Venkatesh Parasuram. So please.
Yeah, thank you, Shivani. That was short and brief and really good. Namaste to all, and welcome to all the participants and the members, and the Board of Governors, board members, honorable guests from the Education Council, CSI members, IFES, GEDC, the supporting partners of this Global Emerging Tech Summit 2021. I'm happy to be the part in experiencing this summit in virtual mode, and would like to mention that this pandemic time has taught us to tweak ourselves in evolving into differential method of learning. Taking it positively, I mentioned this is a boom. Now is the time when there is no border or boundaries for learning and gaining knowledge with the emergence of virtual learning mode. And even better, when they are certified by the professional bodies like CSI, IFES, GDC, and UET, which helps in your career growth. And all this without travel, stay, and from your comfort of your home. Let's embrace this method of learning as sky is the limit, and there is abundant certified knowledge available for you from the lectures during the summit. On behalf of Computer Society of India, I'm happy to have CSI partner with University of Emerging Technology, supported by the Emerging Technology Foundation USA, towards bringing the change through this tech summit. At UET, you have the opportunity to hear from the academicians and industry experts from different countries, bringing their experience and knowledge for the benefit of the student fraternity under one platform, with various emerging technologies like artificial intelligence, machine learning, cybersecurity, cloud services, mobile computing, and to name a few top. And most importantly, you would go through the role-based experience learning for the benefit of an understanding of about the CSI to all the participants who are from different countries. Computer Society of India was formed in 1965 and is a premier professional body with many members from the India's famous IT industry leaders brilliant scientists, academicians, and educational institutions. The CSA has been instrumental in guiding the Indian IT industry down the right path since its formative days. Now, the need of the hour for today is acquiring knowledge from any source what you get towards the job-ready skills. And at UET, you can see this transformation. I believe in that. All participants for the summit would be hearing from the eminent experts in their respective domains from the series of lectures starting today for the next 3 weekends. And more on AI and ML, the eminent speaker, Bill Vorhies, would be giving that. And I have gone through that challenges in cybersecurity from Shah Zanani, and web service cloud from James D'Souza, mobile app development from Ravi Satar, and digital transformation from Sesha Kishore, and no coding application development from Bharat Kumar. These are the power pack lectures which you will be hearing over the 3 weekends. The details are already shared with all, and I would only suggest please make the best use of it. And let's emerge into the future with the practical, differential, and role-based learning during this pandemic time and also future. All said, with this, I'm happy to announce the Global Emerging Tech Summit 2021 open. Welcome all. Have a power pack session. Namaste.
Thank you so much, sir, for the wonderful speech. Now I take the pleasure in introducing our speaker for the day, Mr. William Vorhies. Mr. Vorhies is the President and Chief Data Scientist at Data Magnum. Data Magnum is a data science consulting organization. He is currently a contributing editor at datasciencecentral.com, which is the leading online community and content website for data science. He has also been the editorial director for many years. In that role, he has authored over 300 articles and white papers, which have been read more than 2.5 million times. Additionally, Mr. Vorhies is an executive board member for the University of Emerging Technologies. Mr. Vorhies is going to speak today on the tools and applications in machine learning and artificial intelligence. What makes Mr. Vorhies' background particularly suited to this topic is he opened his first data science consultancy in 2001. For the last 20 years, since the earliest days of the field, he has lived and helped develop these tools and applications through its period of most dramatic innovation, and now its current period of intense adoption. Ladies and gentlemen, please join me to welcome Mr. William Vorhies. So please.
Shivani, thanks very much for that nice introduction. Let me begin by sharing my screen, and thanks everyone for having me today. Let me get this technical detail out of the way. There we go. Okay, so you know, for a profession that's concerned with accuracy, as data science is, we're really very, very bad at establishing clear definitions. And the poster child for this confusion is the phrase artificial intelligence. So here's an in-joke we tell each other. You know, when we're talking to a customer, it's artificial intelligence. But when we're talking to a VC, it's machine learning. And when we're talking to another data scientist, it's statistics. So this language is very confusing to a lot of folks. And the popular press has frankly hijacked the term artificial intelligence to apply to everything we do in data science, which isn't correct. And it really gets in the way of understanding what we do and how we do it. So today, you know, with every company you can think of rushing headlong into its digital journey, there are just not enough people who really understand what the tools of data science can do, and particularly what they can't do. So whether or not you're going to pursue a career in data science, or just going into a role in business or government or education, you need to understand this field from a data scientist perspective, so you'll be better able to lead smart conversations about the data science projects you're going to encounter. So today we're going to talk about 4 broad areas. We're going to try and clear up this perception that everything is artificial intelligence, and split out from a data scientist point of view, you know, what is machine learning and what does a data scientist think is artificial intelligence. We'll talk a little bit about the tools we need to use, with an emphasis on the most modern stuff, deep learning. We'll talk a little bit about how you learn it and how you practice machine learning and AI. And for just a brief second, we'll talk about where we think this is all headed here. So here's the secret. This field has, I was going to say it's changed name. That's not actually correct. The press has changed the name of our field a bunch of times over the last 20 years. And if you go back to the 1990s, you'll see it referred to as data mining or predictive modeling or machine learning or deep learning. You know, the fact of the matter is the best phrase that most accurately describes what we do in data science today is machine learning and artificial intelligence. So here's the real secret. 95% of what we do is to train models. That is, we are building models that learn by example to predict either a future behavior or a future value. So a future behavior, almost all of that is consumer propensity. You know, why they come, why they stay, why they go, what will they buy next, or predicting a future value like the price of Amazon stock next Monday, or the spot price of oil, or how many widgets I'll sell, or how much that customer will be worth over his lifetime. Or, you know, now that we have image and text, is that a Ford or a Chevy? That image is a Ford or a Chevy, or does that text from the customer say that he wants a red dress or a blue one? So to train by example means we start with data associated with a known outcome. That is, for example, customers who bought in the past, and we know a lot about them. We train the model. We can use both data that we have and data that we can add from external sources. And then finally, we apply that model to data that we've never seen before, potential new customers, to predict who is most likely to perform according to what we've trained. Now, this is a bit of an eye chart, and I'm showing you this not to make you read all of these names of the techniques that we use, but rather so that you'll understand when you hear the phrase decision tree or random forest or logistic regression or neural net or Bayesian analysis, you'll recognize these as part of the data science toolbox. And all of them are machine learning. So if you become a data scientist, you'll learn most of these in some detail. But if you're a business leader and you just want to recognize or recommend data science solutions, you need to know that they're part of our toolbox. Here's one of the most powerful concepts that we'll be talking about today, because you know what? Everything we do in data science answers only 5 questions. And here they are. And if you remember these, you'll always know whether or not a potential business problem is suitable for data. So the first one, is it A or B? So this is classification. And some examples might be, will this machine fail in the next 72 hours? Yes or no? Which brings in more customers, a $5 coupon or a 25% discount? Or if a customer calls into your customer service rep, should I try to cross-sell X or Y? So in question 2, is this weird? This is very much the era, the domain of anomaly detection, which is largely used in all the financial services to detect, for example, fraudulent transactions, but also in the management of your network security to identify bad actors that are trying to break into your system. And it's very much like classification, a special set of classification tools to determine. Number 3 is not sure how many. This is regression. That is, what will the temperature be next Tuesday, or what will my 4th quarter sales be? Now, number 4 is one that not many people think of, and that is, how is this organized? And by that, we mean the data, because there are a lot of ways to tease out the structure of data. So One approach that you'll hear about is clustering, which separates data into natural clumps, which makes it easier to interpret and to analyze. Very important. And then finally, what should I do next? And this is strictly the realm of reinforcement or mathematical optimization calculations. It's a good fit for automated systems that have to make a lot of small decisions without human guidance. It's, for example, if I'm a self-driving car, and I see a yellow light, should I brake or should I accelerate? For a robot vacuum, should I keep vacuuming or should I go back to my station? Or frankly, for human beings, if my inventory level falls to X, should I reorder? So a lot of people think that data science is all about the algorithms, and they always want to talk about the algorithms. But to understand how data science has emerged and broken into such a powerful tool, you need just a little history. So data science was alive and well in the 90s and the aughts, most of it in direct marketing at banks, insurance companies, and large direct marketers. But prior to 2000, we had pretty much all the tools we have today, but we were held back by two factors. First, as you might imagine, was simply the raw compute power. But the second problem that we had before 2007 was even more important. And that is that we could only hold data in relational databases, meaning that it was held in very small fields, mostly numericals with a few text fields. And as you undoubtedly know, relational databases are slow to change. They're tough to get data into and out of. If you have a new data source in relational database, you have to fully map its presence in your database before you can get to use it. And sometimes that takes weeks or months. But what happened in 2007 is we had the arrival of big data. Now, by the way, big data is another naming fiasco that we need to take responsibility for, because it's not about just big. It's not about just volume. More importantly, it's about variety, which in our language means image, video, audio, text, unstructured or semi-structured data that previously did not fit in a relational database. And then finally, velocity, that is data in motion, streaming data from sensors that are the data sources for our Internet of Things applications, or real-time streams of financial data like stock prices. So our big data database, known as NoSQL, which simply meant at the time that you couldn't use SQL as a query language on it, was a new family of databases without the rigidity of relational databases. The first one, of course, you probably have heard of is Hadoop. Of course, these days, what you'll see is that relational databases and NoSQL databases have come back together and been put together in families of databases that you can, in fact, use SQL on. But the most important thing here is actually not that Hadoop and NoSQL could store unstructured data, but that in point of fact, it was a method for making multiple computers work as though they were one. This is where we got the ability to do massive parallel processing, which almost immediately rapidly accelerated our compute and became the core of cloud compute for data science today. So here's a little bit about how this emerged. You know, on the bottom axis, we're going to talk about whether or not the insights that a particular technique gives you are specific, that is, percentage-wise accurate, or whether or not they're simply directional. And on the vertical axis, we'll talk about the different types of data that emerged and how they have facilitated the various things that have evolved in data science. So starting immediately, we got data lakes, which was our ability now, instead of having relational database, if we had a bunch of data that we wanted to take a look at, we could dump it into a Hadoop database, a NoSQL database, and play with it, which became very powerful and the first in putting some unstructured data back into our predictive modeling. Then recommenders, also based on semi-structured data. We got these systems that could analyze huge volumes of web logs and do it essentially in real time, so that we could recommend to our customers what they should buy, what they should watch or read, who we should date. This also meant that we were able to now start natural language processing, which in the beginning was, for the most part, just big bag of words analysis that was mostly used in sentiment analysis. That was that caller to the call center satisfied? Did you think the product was too expensive? Was it the wrong color? Was the food good? Was the service lousy? You could get generally directional information out of a bag of words. But today, obviously, natural language processing is much more sophisticated, and it allows us to interact with Alexa and Siri, and even to have the more important platforms that you know of as intelligent automation or robotic process automation, which is often where companies these days start on their digital journey. Now, we haven't talked about data in motion, but the Internet of Things is based entirely on streaming data, which can be part of, and frequently is, input to very specific predictive modeling, and is part of edge computing. And then finally, we have our new non-traditional techniques in machine learning. And this is where we get the new artificial intelligence techniques, deep learning, convolutional neural nets, second generation neural nets that underlie the advancements in speech, text, and image processing, and reinforcement learning, which are the techniques that enable self-driving cars and let computers win at chess. Now, here's how the popular definition of artificial intelligence and data science come together. Because many people think that we've only just suddenly arrived at artificial intelligence, and that's simply not correct. In point of fact, this has been an altogether evolutionary process, as almost all science is. So we built on handcrafted expert systems, we added machine learning, we added our ability to do big data, and now we're adding deep learning, which are the second generation neural nets like convolutional neural nets and recurrent neural nets. So let's come back to artificial intelligence for a minute. So there have been a lot of efforts to define what AI really means, but most of them are contradictory, and they just end up missing the distinction between the popular definition and what we data scientists think of as actual artificial intelligence. And our founders of artificial intelligence and machine learning have thought about this for a long time. A lot of you know about that's like 71 years old now, and that is, can a computer convince a human that they're communicating with another human? Another test that was proposed was by Steve Wozniak, who's you may recognize as a co-founder of Apple. And he proposed that we'd have artificial intelligence when a robot could walk into a strange house and find all the ingredients and the tools necessary and successfully make a cup of coffee. And then later on, Robert Getzel proposed that we would have artificial intelligence when a robot could enroll in a human university and take classes in the same way as humans and get its degree. Well, actually, this is getting pretty close. The Chinese back in 2017 had a robot that competed with grade 12 students during their country's national college entrance exam. And it got 105 out of 150 points. It was below average. But on the other hand, it finished in 22 minutes, where most students took 2 hours. So not a real win. But later in that year, also in China, a different robot passed a written test of China's national medical licensing exam, and the robot scored 456 points, which was 96 points higher than the required mark. No word about whether or not that robot was put into private practice. And then finally, we've got folks like Nils Nielsen, who's one of the real founders of artificial intelligence research. And he proposes that we'll know we have artificial intelligence when, in fact, our AI can take over the job of actual human beings and before them can either fully or partially replace them. And of course, with, for example, intelligent automation today and chatbots, you'll see that a lot of, for example, customer service representatives have in fact been replaced by our AI. So the way I like to think about it is actually to be a little broader than these examples. And the reason I like to spend a little time on this is that AI is supposed to demonstrate human-like capabilities and to be able to replace humans in that activity. And because it informs what we expect our AI to be able to do, what human-like capabilities it will need to have, I like to start with this kind of anthropomorphic model. And on the left, you see it'll need to see, which are still video images. It needs to be able to hear, that is, receive input via text or spoken language. It'll need to speak, that'll be able to respond meaningfully to input, same language or frankly any language. It'll need to make human-like decisions, be able to offer advice or new knowledge. It'll have to learn, it'll have to change its behavior based on changes in its environment. And ultimately, it'll have to move or manipulate physical objects. So here's how this actually lines up with our new technologies. So I realize this is a bit of an eye chart, and I'll let you follow along the red lines for yourself, but I will just talk about these 6 new modern tools that data scientists think of as artificial intelligence in our field. So image processing is largely handled by convolutional neural nets, that we'll talk about in a minute. Language processing by recurrent neural nets that have evolved into more advanced forms. Question answering machines. You may remember IBM's Watson that won Jeopardy. We're going to talk about generative adversarial neural nets, which can be fun or can present a threat. Reinforcement learning, of course, which is important. And finally, robotics. So let me put deep learning, which was missing from the previous slide on purpose, is that the deep learning is not itself a specific category, but rather a group of new tools that we're using, though it's one of the most common phrases that the press uses. What I want to show you is that artificial neural nets have been part of our toolkit since the 2000s or even the 90s. But what's happened is that we have expanded on them and now created more elaborate architectures for these neural nets, and we now refer to these as deep learning. So I know this is an eye chart. What I want to show you is that there are many, many, many types of artificial neural nets, particularly in this new second generation. If you look up at the nodes on the left are the input nodes, and then as you move left to right, the output is on the right-hand side. And what we call a deep learning or deep neural net is one that has hidden layers in between the input layer and the output layer. And as you can see, almost all of these now have many hidden layers. So there are at least 27 different types of neural nets. Most of the action these days is in the recurrent neural nets, which now include LSTMs and BERTs that we'll talk about in a minute toward the top, or the convolutional neural nets that you see diagrammed in the middle, or the generative adversarial neural nets that you'll see down toward the bottom. Just remember that deep learning means adding hidden layers to a neural net. Now, some deep nets may have just, say, a half a dozen hidden layers. But for example, back when Microsoft first reached the ability to identify images with the same accuracy as a human, that CNN that they used at that time had 152 hidden layers. And the problem is, of course, that every time you add a hidden layer, you increase computational complexity and also weaken the signal. So adding more hidden layers is a kind of a devil's choice. You're better off with fewer, but many times it takes many more to do that. So now we're going to spend just a couple of minutes on each of the different types of new deep neural nets. And we'll start here with number one, which is image processing, relies mostly on convolutional neural nets. Now, remember that our tools really can't do anything that hasn't been reduced to numbers. So the purpose of the front end of a convolutional neural net, marked here as feature extraction, is to discover the features hidden in each RGB pixel of an image, convert it to a numerical value, and create increasingly sophisticated and deep numerical vectors that will then be put into a classifier that let us tell whether or not this is a dog or a cat or a boat or a bird. Now, typically what would happen is we would scan the image at left, starting with, say, a matrix of 32 by 32 pixels, could be bigger, and then develop vectors for each of those 32 by 32 grids. The second convolution might very well be 28 by 28. The third feature map might be 14 by 14, and so on through the hidden layers until you get down to a point where your classifier on the back end can reliably determine whether or not the image is what you say it is. Now, a couple of things. Because we are reducing all of these images to numerical vectors, one of the interesting things you want to keep in mind is that I can also run them backwards by inputting a numerical vector on the right-hand end and actually generate an image on the left-hand end. Once again, every time we add a layer, we add complexity. So you might think of convolutional neural nets strictly as automatic feature extractors. The problem is that they are not necessarily interpretable by human beings. So you see here, these are 3 different layers of feature extraction from that car. And of course, no human being could really make sense of those images that have been produced. Also, remember that it takes a lot of labeled training data to train a convolutional neural net. You could probably get acceptable performance with about 5,000 labeled images per category, but it would take 10 million labeled examples per category to match or exceed human performance. So it's really kind of a brute force approach. And now you can see why the speed of compute and our ability to spread the compute over multiple machines in massive parallel processing becomes so important. However, just remember that time and that time on the machine, which you'll probably be renting from Amazon or Google or someone like that, has a cost associated with it. So it's expensive and time consuming from several days to several weeks of runtime to train a particularly large convolutional neural net that can meet human levels of identification. And that much labeled data generally just isn't available. There are, however, 2 approaches these days to doing CNNs. Of course, the first one is doing it from scratch, which we just talked about, where you'd need thousands to millions of items of label training data. You'd need huge amounts of compute. The problem would stretch over days, but the model accuracy can be extremely high. Now, the problem with this approach, of course, is that it requires real experts and time. And frankly, there's a scarcity of folks with these skills. Also, it's not enough just to show your convolutional neural net one image of your target item, but rather you have to allow for all of the different ways that the CNN might actually end up seeing the item. So it can be translated or rotated or brighter or dimmer or even larger or smaller. You know, is the cat the same color? No, there are different colors of cats, and you have to represent all of those if you want your CNN to train adequately. The second approach is one that a lot of businesses have adopted today, and here we owe a debt of thanks to Microsoft, Google, and Amazon, who have provided very, very large foundational convolutional neural net models that are, which they'll allow you access to, which you can use as the basis for what we now call transfer learning. Now, basically in transfer learning, you would take one of the master convolutional neural nets that's already been trained by one of the big organizations. You would simply cut off the classifier on the back end. You would add the specialized images. For example, if your data set includes, I don't know, specialized tools or specialized equipment or pictures of a particular type of plant, you would add those to the database. And then now you can rerun and retrain the CNN, which already has many of its convolutions already trained up. And this is much faster. You can do this with perhaps just a few hundred or a few thousand images, and it's quite fast. So this is a way that a lot of folks are now doing convolutional neural nets in business. Also remember, however, that all of this powers facial recognition. And so facial recognition has been getting a lot of bad press lately. And so here's the good news or the bad news, depending on your point of view. Because convolutional neural nets can be confused by just a little bit of noise. So, for example, that hat on the left, you can buy that today on the internet as a way of foiling facial recognition system cameras. And the stop sign on the right is even more interesting because just a couple of these pieces of tape on this stop sign would cause an autonomous vehicle not to recognize this as a stop sign. As a matter of fact, this particular example, which was developed in 2017 on one of the largest Microsoft CNNs, actually makes the car think that the stop sign is a banana. So for whatever reason, the features active for banana corresponded to those pieces of tape combined with the stop sign. So I guess the good news is, yes, you can hide from facial recognition. The bad news is you have to watch out for noise, and particularly that, in point of fact, bad actors could actually weaponize this noise to fool self-driving cars or other autonomous systems with just a little bit of tape. Okay, number two, natural language processing. And the naming convention for these deep neural nets, which started as recurrent neural nets, have now evolved through LSTMs, which means long short-term memory. And finally, today, you would probably use a variation called a bidirectional encoder representation transformer, or BERT for short. But they are all developed from the recurrent neural nets. Now, these types of problems and this type of technique is best used in sequence problems. So text and speech falls in that category. Since the next character or the next word in any stream of text is likely to be logically related to the one preceding it. So RNNs handle the understanding of text questions as well as the formulation of complex responses. They're also good for forecasting and time pattern recognition problems like prices or stock values or sales forecasts, and also for gameplay. So where convolutional neural nets relied on spatial relations, recurrent neural nets process information as a time series in which each subsequent piece of data relies in some way on the data item that came before. Now, every time we need to increase the total time needed to remember, that is the number of game plays, for example, we need to add a layer. And every time we add a hidden layer, we increase the computational complexity, the time to train, we weaken the signal, which makes it harder to train. And so these evolutionary upgrades to RNNs like LSTMs and now BERTs have all been designed to address some element of these problems. However, in 2016, so it's been 5 years, we hit 95% accuracy in a robot being able to accurately interpret human text and speech. So that almost instantaneously blew up this market that includes chatbots. It gave us Siri and Alexa. It gave us the ability to communicate by voice with our phones and other devices. And it gave us intelligent automation, which is also known as robotic process automation. And that's often the place where companies these days start their digital pursuit in AI and ML. That's the new low-hanging fruit. Now, this third type is actually a lot of fun. And despite that it's got this huge name, generative adversarial neural nets, these are designed to make training more efficient. They're still relatively young in their application, so there's a lot to be learned yet here. But remember that convolutional neural nets can be fooled by just a little bit of noise so that they can be intentionally hacked. So consider this example. Let's suppose that you wanted to guard the safe where you were holding all your valuables with a retinal reader. But in point of fact, the retinal reader based on a convolutional neural net model could be hacked. GANs are a strategy for creating CNNs that are much less likely to be fooled. So here's the basic concept. There are two convolutional neural nets that are put in competition with each other. The first one is known as the discriminator, and its task is to correctly classify an image that you're training it for. The second generator. Remember that CNNs can be run backwards from random seeds to create images, and that's what the generator does. So the task is the generator's task is to produce images that will fool the discriminator, and they battle it out until they reach an evolutionary draw in which the two systems are optimized against each other. So here, for example, was an early example in which the discriminator was trained to recognize this particular school of French painting. The generator was set the task of generating fake French paintings from this period to fool the discriminator. And they went at it for millions and millions of generations until finally the generator could produce images that were almost to the point where the discriminator couldn't tell the difference. So when that ability to discriminate reached zero, then the two systems were trained, and now the the learning system, the discriminator CNN, could almost assuredly not be fooled by a little bit of noise. Still, these are very difficult to train, but they're as close as we've come to having machines that learn by themselves without human intervention. Unfortunately, these GANs are also the ones that enable today's deep fakes that I'm sure you've all read about. That's a problem that it creates for us in a culture where the truth of photographic evidence is being called into question. But it also allows for extremely sensitive video analysis to define patterns that were frequently or formerly undetectable. And number 4 in our new toolbox is reinforcement learning systems. And of our new artificial intelligence disciplines, up to this point, they've all been based on deep neural nets. But that's not necessarily true of the next 3, including reinforcement learning. Reinforcement learning is by de facto the third leg in machine learning, alongside supervised and unsupervised learning. And it is a method of training a system to recognize the best outcome in direct response to its environment. Now, there's not a single algorithm here, but a group of custom applications. Yes, some of them can be powered by deep neural nets, but others of them don't need deep neural nets. This is the core technology in self-driving cars. It's the core technology that allowed computers to win at AlphaGo and to beat us now at a whole variety of other games. So here in this diagram, basically what goes on is that there are 2 things that you can do. Prediction, to dramatically simplify this. That is, for example, how much reward can I expect from every combination of future states? That is, how much can we hope to collect from delinquent accounts based on the following set of steps? Or control, which is autonomous vehicles, or gameplay, that is by moving through all the possible combinations of an environment and acting with the environment, find a combination of actions that maximize the reward. That is, win the game or don't crash. So reinforcement learning actually comes from the natural world, and our little newborn antelope here is the poster child, because like that antelope that learns to stand up and actually run within about 4 or 5 minutes of the time it's born, that's an evolutionary requirement for survival. And it's pretty much the same thing for recurrent neural nets. So the key to understanding when to use a reinforcement learning system is the data for learning doesn't currently exist. Remember, we talked about the labeled data problem. Or you don't want to wait to accumulate it because the delay might be too costly, or because the data may change rapidly, causing the outcome to change more rapidly than a typical refresh cycle can handle. That might be particularly true in a car looking at a new roadway that it's never seen before if it's operating in an autonomous mode. So there are lots of details here. I'm going to skip over most of this slide, other than to say that reinforcement learning is still very early in its application. There are a great many challenges in each effort to train one. These are the general names and descriptions of some of those. And we fail to train on our error RLS systems about 70% of the time. However, when they do, they are an interesting and excellent solution to this particular type of problem. Now, the 5th type of knowledge or technique, rather, that we talked about in artificial intelligence is question answering machines. And you may have noticed that so far we've been talking about decision-making systems that have no knowledge of content beyond what they've been shown in the training data. But our AI college student or robot employee or robot barista still needs to have some knowledge to apply to their environment. So if you remember this story, the Watson that lives in our imagination in 2011 actually won against human contestants in this popular game show called Jeopardy! Of course, it actually took IBM almost 7 years with a team of about 20 data scientists to develop it, so it was no slam dunk. And by the way, Jeopardy! Watson did not win in a walk-off. It made plenty of its own mistakes. So why haven't we heard more about Watson in the popular press today, or question answering machines? Well, what actually lives in the imagination of people in the popular press about this particular technique is actually old technology for us. And it's a good illustration that not all of the promising new approaches in data science can be a home run. This is a bit of an eye chart that describes the working of Watson, but here's the general story. You know, the dream of Watson was to be able to deposit all the knowledge for a particular domain in a database. Think taxes or chemistry or medicine, and have not just a search engine, but an engine that would find obscure linkages and combine them in a way that it could deliver not only a menu of possible answers like Google, but the one best answer, and perhaps one that we haven't thought of before. So the distinction with search like Google delivers you a menu of possible outcomes that you can select from. A question answering machine is designed to deliver the one best answer that best meets the problem that you've posed. So the requirement here is that humans load and continuously curate its knowledge base, which is called the corpus. And they also load a variety of test questions designed to illustrate for the QAM the relationship between inquiries and topics. And then the QAM should be able to go beyond those examples by creating its own tests and delivering its own results. So why did I say this might be a dead end? Well, not really a dead end, but for example, by 2015, IBM had already invested north of $15 billion in Watson. And you used to hear an awful lot about Watson being used in hospitals for really advanced patient treatment, but that's been pretty much brought to a halt. IBM was working with Sloan Kettering Cancer Center and also with MD Anderson on projects like this. And both of those projects have been pretty much abandoned. And the reason is that it required doctors to continuously load important information into it, but more importantly, to remove information that was no longer accurate. And that just took a lot of time. So Watson and the concept of question answering machines will work in domains that are relatively constrained, think taxes, tax law. But in these open-ended applications, it's proving to be very expensive and time-consuming to try and keep up with the body of knowledge. And finally, we've got robotics. So these days, yes, you can make robots learn by using reinforcement learning, but that's not actually the way most robots are programmed today. Mostly it's just really clever engineering based on physics. But still, we need to be able to make our artificial intelligence systems sufficiently mobile that they can interact with us in our own environment. Now, the problem, of course, is how smart it is versus how useful it is. We have gone a ways toward combining artificial intelligence into robotics, and that's an opportunity for you that are just starting out in this field. But as this image is meant to point out that robots don't always have enough AI in them. In this case, of course, the self-floor cleaning robot couldn't recognize the dog poop and smeared it everywhere. So, oh, if it only had a brain, huh? Okay, so those were our 6 new data science techniques that data scientists would consider the building blocks of artificial intelligence in data science. But now let's talk about a little bit about how you're actually going to learn and practice this. Now, first of all, let me tell you that despite the excitement that we may have created around techniques, that probably 75, 80, 85% of the applications of data science in business today are not these techniques. They are good old machine learning. Tell me what the customer is going to buy next. Tell me when the machine is going to break down. Almost all of it classification, though it is based on now on increasingly on big data categories of unstructured and semi-structured data. The other thing I want to impress upon you is that data science is not like learning a programming language. You know, a little history here. If you go back to say 2000 and you were to come into the field as I did, what you would find is a field dominated by 2 companies, SAS and SPSS, now part of IBM. And in those days, you wrote models in SAS and SPSS proprietary code. Now, very rapidly, by 2005, 2007, both of those companies had moved away from code and toward drag and drop automated coding platforms, so that the requirement to code was greatly reduced. But you still got access to all the model hyperparameters. Now, we haven't talked about hyperparameters, but let me point out that every one of our techniques has a whole variety of tuning metrics that we call hyperparameters that need to be adjusted by a data scientist in order to operate as accurately as possible. So one of my personal concerns about coding is that it tends to distract you from the requirement to tune the hyperparameters. I got you up into the middle 2000s with the first incoming of drag and drop platforms. Then we hit in 2007 or 2008, we introduced R. And the teaching universities largely abandoned the tools provided by SAS and SPSS in favor of teaching data science by code using R. R was replaced by Python, and today, if you're learning data science, you're almost surely going to be taught Python. But this graph on the right, which you'll recognize as one of Gartner's standard magic quadrants, shows the leaders in these analytic platforms today. And what I've done here is all of those circled in orange or red are platforms that are very rapidly moving back toward semi-automated or fully automated data science applications. And that's not a bad thing. They are no code like Data Robot or low code like SAS or Alteryx. And because there are now so many models to be maintained, this level of automation allows you to, a single data scientist to do the work of a great many data scientists in less time. The other thing that you need to be aware of is that, you know, in the beginning, the data scientist was expected to be able to do it all, to use all the techniques, to select and assemble all the required databases, to train and create the models, to move those models from test into production. But the world today is just too complex for any one data scientist to master all of this. So even on the technique side, the application of your skills, you'll see that data science skills are splintering into these 4 groups. There's the traditional customer behavior and risk modeling. That's probably, again, 75 or 80% of the opportunity today. There's physical system modeling, anomaly detection, preventive maintenance. That's an increasingly important area. Speech, text, and chatbot, that's a separate specialty today, as are image-based recognition and autonomous vehicle platform systems, a separate area. So during your education as a data scientist, if you choose that, toward the end of that, you'll want to think about which of these you'll want to specialize in, or alternatively wait until you get to your first job and then train up after that. The second split here is between data scientists and data engineers. And increasingly companies are establishing data engineers as a separate category of worker who handles all the setup of the database, the accumulation and cleaning of the data, and then the movement of the models into production, so that the data scientist can handle just the data science portion. All of these, by the way, the salary rates for these are surprisingly pretty much the same. And while you're probably aware that the demand for data scientists and data engineers has doubled over the last 24 months, you should also be aware that the supply, you all, has also doubled over the last 24 months. So while the pay remains very attractive, it's the skills that you have or will get are no longer in shortage, and that'll make it a little more challenging. So what we haven't talked about, now that we're down to the fun stuff here, is artificial general intelligence, and whether or not you think of that as the Terminator or as Rosie the robot. We know from our little modeling exercise earlier that a real AGI system will have to display human-like general intelligence, not just tied to a specific set of tasks. And it also has to be able to generalize what it's learned, and especially to extend those generalizations into contexts that are qualitatively quite different from what it's seen before. So how close are we to achieving artificial general intelligence? Well, there's really no agreement. There was a panel of 7 very highly regarded experts recently asked the same question, and their guesses ranged from 7 to 70 years before we achieve AGI. The median was out around 2040, but it sounds like this is going to be a lot harder than we think. There is an interesting thing going on about where we move from here. Now, if you're a data scientist in business, you'll want to keep up with what's going on in these areas. But frankly, unless you pursue a PhD, you probably won't be researching or advancing these areas. But there are 4 major pathways along which data science is advancing today that are really just starting, that only are just beginning to have demonstration ability. And so in the middle, high performance computing, you read about this all the time. This is the ability to train larger and larger models more efficiently. So the faster that we can push our deep neural nets through the compute stage, or spread them out over more and more boxes, the less expensive they'll be and the more of them that we can do. Quantum computing, I think, probably speaks for itself. We all know a little bit about quantum computing. I don't know if you're aware, but you can actually go out on IBM's or Microsoft's quantum computer today and train on it. You'll need to ask for permission, but it's generally granted. And you can use their new quantum computing programming language to experiment with that. Only if you're very motivated. Obviously, that's a very complex area. At the top, TinyML is a very rapidly expanding area relating to our ability to shrink down the circuitry, the hardware circuitry that learns, that can be trained so that it's small enough and can be run with a small enough battery to be put in a very tiny object. like a phone, or like a key fob on, say you wanted to monitor your pet, like your dog, or on any sort of IoT application. So these are the extremely specialized, very small, very low power chips that are becoming available even as we speak, mostly for IoT applications. Now, the one that I skipped over here is the one that I'm betting on personally, and that's neuromorphic spiking neural nets. And I know that's a mouthful, so let me talk about that for just a second. Our neural nets, our deep neural nets, are based on this fiction that they are supposed to look like the way the brain is organized. And that because what you'll see is that all the neurons are attached to all the other neurons, and that when any neuron fires, all the neurons fire, and that's just not the way the brain works. Also, if you look at the energy signature from a spike of an actual brain neuron, what you'll see is that there's a large initial spike, and then that there are several smaller spikes. So we really don't know yet whether or not there is additional information contained in those smaller spikes, or whether or not it's contained in the height of those spikes, or maybe it's even contained in the distance between the spikes. So spiking neuromorphic neural nets are basically advanced chips that are designed to utilize this spiking technology and to therefore break through into another area of data science. Now, there are actually companies that have these in production today. If you look at Brain Chip Holdings, it's actually listed on a stock exchange. You could invest in it today if you wanted to. But their chips show some really, really interesting behaviors. For example, when one of their chips was exposed to just a series of a moving image of a freeway in which cars were passing, after just a few minutes of observing the cars passing on the image and without any external programming or impetus, it started counting the cars. These are also being used now in some casinos in Las Vegas, where they've been programmed into the image watching the cameras over the table, where the neural net can actually learn the game and actually spot cheaters more efficiently than human beings can. So if I had to guess about a technology that was going to take data science into the next generation, of course, you can't ignore any of the four that we've talked about, but I'm particularly excited about these neuromorphic neural nets. So let's bring this conversation to a close. I think we all understand that artificial intelligence and machine learning is in fact the next great lever for corporate growth. There have been many, and now we are poised on this brink of implementation. So let's talk about how this happens, because managers in business are used to managing people, processes, and technologies as separate entities. And that's something that business executives are comfortable with. And over the recent past, say up through the 90s, the three most major innovations for improving business were, you may recall, process improvement, re-engineering, and then even business intelligence. So those are all concepts that can be reasonably well understood by reading a good book, and their adoption by corporations reflects that. As a business manager would go home, he'd read a book, and the next thing you know, you were in one of these projects. But now data science is by definition more complex and requires more knowledge of data scientists. And it also requires knowledgeable business managers to identify targets, to form the specialized teams that are required to actually implement AI ML solutions. So through about 2017, the underlying algorithms and the data and the compute were changing so rapidly it was difficult to keep up. But for roughly the last 3 years, we have specifically exited the era of rapid innovation, and we're now entering the era of full-time implementation. Now, it's not about getting some data scientists to sprinkle some AI ML on your organization. It starts with your analysis of processes that could be improved, your understanding of the many ways in which AI ML tools could be integrated into your processes for improvement. One of them that we've spoken about a couple of times, just because it's so popular these days, is robotic process automation. This is the new low-hanging fruit for implementing AI and ML as a good starting point for many companies. Not necessarily the only point, but certainly one that's become extremely popular today. So I hope this has helped you better frame the environment that lies ahead for you if you choose to pursue data science, or to become more successful business managers who have now some knowledge and skills to recommend and implement data projects. With that, we'll be happy to entertain a few questions.
Thank you so much, sir, for the very insightful lecture. I hope all of you enjoyed the session. I surely did. We have a lot of questions raised by many of the members in an audience. Thank you all for being so attentive, but we are really sorry that due to the time limitations we have, we would be able to address a few for now, and then we'll try to answer the remaining questions individually after. So we have our first question. Someone in the audience wants to know, what is the difference between artificial intelligence, machine learning, and deep learning?
Uh-oh, I hope they asked that question early in the presentation and not late. Otherwise, I really messed up.
Yes, sir, it was asked during the starting of the presentation. Okay. Okay, so another question is, what are the job opportunities available in artificial intelligence and machine learning?
Okay, so we talked a little bit about this in the presentation, and I would make a couple of points. First of all, the field is rapidly splitting between data scientists and data engineers. And don't be afraid of taking the data engineer path, even though you'll be basically dealing with the infrastructure and the implementation of the models that are produced. The salary levels are roughly the same as data scientists today. There are not enough data engineers to go around, and it can be a very satisfying career. In terms of the techniques, almost all the business classifications, business applications remain in classification of some sort of consumer behavior. What's interesting, I think, is, we talked a little bit about accuracy. It's interesting. Remember that accuracy in a model, if you have 50% accuracy, there's a coin flip, so that's not much good. Generally speaking, when we're dealing with consumer modeling, if we get to about 70%, we're happy. We can get higher than that, but 70% is a useful model. But if you're modeling things that are physical phenomenon, like a manufacturing process or a machine, you ought to be able to get to 90, 95, 99%, because what you're really doing is just describing the rules of physics. And so I think it's telling that whenever you get human beings involved, our predictive capability just isn't as good.
Okay, so most of our attendees are college-going students and recent college graduates. So I'm sure all of them were interested in knowing the job opportunities in the field. Thank you for answering that. The third question is...
I didn't follow the question.
Yes, sir. The question is, a lot of people seem to fight against or be fearful of artificial intelligence. Why do you think that is?
There's a lot of conversation about ethics in artificial intelligence these days. And it deserves a place. Most of the conversation is around convolutional neural net solutions and recurrent neural net solutions. And the reason is that as we showed in picture form, you can't really tell what the machine learning application is focusing on to make a decision. Is this person friend or foe? You're well familiar with the situations in which it's misclassified people by race or by sex. People are also worried about whether or not there is a hidden bias in making important, for example, financial decisions like, do I get the loan or do I not get the loan? And those are legitimate concerns. Almost universally, as a data scientist, I would tell you that those could be solved by training with more data until you get a trained model that no longer shows those defects, because you can test for those defects. I understand that people who have only read the popular press, and the popular press is just as much to blame here as anything, have read a lot of bad stuff about artificial intelligence. But once you're on the inside looking out, I think you can see that almost all of these problems have technical solutions that you as data scientists can address.
Okay, so one other attendee has asked, what are the major impacts of chatbots in the upcoming days or years? Impact of chatbots. Yes, sir.
Oh, just chatbots? Well, okay. So basically we're talking about voice recognition systems. So of course, first of all, many of us are now used to, in text or voice, communicating with customer service reps or posing questions to websites in the form of natural language, which makes it very easy. It also makes it possible for the receiving company to reduce labor cost and to handle those inquiries much more efficiently, especially, for example, during hours when it's just not possible to have a human being in sufficient quantity to answer those calls. I think the more interesting aspects of chatbots are actually in, for example, the instantaneous translation of one language to another, which is going to make a big difference in our ability to break down barriers between our different cultures and countries. And then finally, though it's not technically a chatbot application, our ability just to speak to our devices in natural language makes our whole method of interacting with them so much easier. So those are the big ones.
Okay. So one of our research fellow with the Emerging Tech Foundation has a question. She wants to know, what are the ways by which the problem of shortage of specific real world data for unconventional models can be solved?
Okay, I'm sorry. Give me the question one more time, please.
Yes, sir. What are the ways by which the problem of shortage of specific real world data for unconventional models can be solved? How can we solve the problem of shortage of data for the models?
Oh, I'm sorry. Okay, Shivani, I beg your pardon. Shortage of data. That's a problem. In point of fact, there are actually types of, there's a whole industry within, sub-industry within data science that has sprung up to create low-cost labeled data so that we could get past that problem. In image recognition, it's particularly difficult because right now, pretty much all the images have to be labeled. So you'll have to find a low-cost labor source. Many of these are hosted in low labor cost countries where actual human beings go through and label images on your behalf at a cost. Natural language processing tends not to have that problem just because there is so much text available. But now when you are talking about the more traditional customer propensity modeling, there simply is a minimum amount of data required. For simple consumer modeling. I used to tell my clients, if you give me 500 data points, I can give you a general idea. If you give me 5,000 data points, I can give you a pretty good idea. And at 50,000 to 500,000 data points, I'm really comfortable that I can give you a pretty precise answer. So one of the areas where this becomes a problem, and you saw this in reinforcement learning slides, is if the phenomenon that you have is new and no data has yet been created, you're going to have to frankly wait until some data is available, or alternatively use an RLS technique. It's also possible to find value in low accuracy models, but that depends on the particular application that you're working on. I guess the real answer is there is no direct solution to having just a little bit of data. You have to have enough data to give you a reliable and repeatable solution.
Thank you, sir. Let's take one last question for the day. Sir, could you please brief us on the future of artificial intelligence?
Okay, well, I was hoping you were paying attention when I talked about the 4 major thrusts into the future. That's the strong compute, the hypercompute, the neuromorphic neural nets, the tiny ML, and of course quantum. So we spent a lot of time on neuromorphic neural nets. Quantum will have its own interesting set of problems to deal with, but you should also be aware that quantum is able to train traditional deep neural nets. So when we do finally get quantum, the whole issue of taking a long time to train a convolutional neural net will completely go away. Essentially, they'll be instantaneously trained. And tiny ML, I think, has a big future in consumer applications and in industrial IoT applications. And I would look to those 2 areas in addition to neuromorphic neural nets as the direction of the future.
Okay, thank you, sir. I hope Mr. Vorhies was able to answer all of your doubts. I know we still have a lot of questions, but due to the time constraints, we won't be taking any further questions. Now, moving forward, I want to invite Mr. Prasad Mahudri, CEO, University of Emerging Technologies, to present his thoughts on the opportunities in emerging tech. Sir, please.
Thank you, Shivani. Thank you, Bill. It's been a wonderful insight into AI/ML. Bill and I share a lot of friendship for a long time. Actually, and he's been always amazing to me. And I can share a small anecdote. What are the odds that you walk into a bar in Netherlands and you talk about data science, and the other guy knows Bill? Okay, and I talked to somebody, I know Bill Vorhies, because he has been so popular on Data Science Central. And I would say that, a lot of people, a lot of data scientists, upcoming data scientists have known Bill for a long time because he has been a big champion of data science. In fact, for a lot of people who don't know Bill, that Bill has started a predictive modeling company in 2001, 2002, when nobody even realized what is predictive modeling is. So, he has been a champion for a long time, even before the so-called parallel computing and big data came up. He was doing that, and I've been associated with him. I'm very thankful to that. Thank you very much. And also, I would say thank you, Venkat, for really supporting this. And I thank everybody. But again, I think my main focus right now is to actually give you some insights into what is this University of Emerging Technology is, and what are the opportunities, and how can you get something out of it. First of all, as Shivani said in the beginning, we are all about evangelizing, educating, empowering, enlightening, and of course engaging people into emerging tech, because emerging tech is a must for us, down the line, and everything is changing and people have to move into that. And the traditional universities and colleges cannot cope up with the pace and the volume of teaching, teaching abilities and the volume. They cannot handle the whole volume at all, we feel. So that's why we thought there could be a university that can actually complement in what they're doing right now. So what we focus on is basically role-based education and experiential learning. I'll come to that in a minute. And then also, there are other problems that we're trying to solve, like, camaraderie, like real-time shared boards, and also labs, etc. But anyway, right now, what we offer to people is a short certificate courses. Also, I want to say these are not for credit. And the short certificate courses could be internships, practical trainings, and bundled, into micro degrees, and then role-based and deployable. That means any course that you take that should be applied into the real industry, and that means it should be really applicable, deployable skill that the people could learn, right? So absolutely, we want to be more applied technology than just technology. That's what the deal is. And also what we feel is there's a lot of upskilling and executive education and engineering and combination of engineering and management is possible. And that's what we are also promoting right now. So we will come up, we'll give you the details if you can contact us down the line, and also the websites do a great job in explaining them. But definitely these are the two things that we are right now promoting and delivering as well. And there are other things that we are also doing for some of the colleges, that we are picking up their courses, and we are teaching them at their curriculum and under their supervision, but giving all the labs, people, teachers, etc. The best thing that we have and we want to do is that providing academic enablers, teaching assistants to almost 24/7, so that people can learn these things very easily and be successful. And also what I say is, anything that is taught at emerging tech has to be of experiential learning. What is experiential learning? Experiential learning is project by top down, a project by bottom up. That means you have to learn the application, not just the theory. And that's how we want to teach, so that you learn better and you can apply better. So there are two things to this. One is the teaching itself, and the second one is the lab. So we have 24/7 lab, our own labs, and also we control, we have our own computer on the cloud. That means the labs. Basically, you don't have to worry about your antenna or not an antivirus, not installing something, some kind of a problem here and there. No, that DL is missing, this Java version is missing. All that we want to take out of the students' problems, and then give them a lab so that they can actually learn the real thing rather than worrying about all other problems. So basically, we are giving 20 live labs, live support. There will be academic enablers. And then we have a computer on the cloud. And we also have, I'll show you some screen prints. We also have a real-time shareable whiteboard, especially when you're learning online. It's always a problem that people have no interaction with other people. And then the sessions, sometimes you want to collaborate and learn more, because you don't see anybody physically. It's all the more important to have a shared board where you can talk to other people and also share your ideas, brainstorm and all that. So that is also being given. So I think we have a lot of all these features actually will really help the role-based education. So if you see what the unique features of University of Emerging Technologies, we have role-based education, experiential learning, and you will have projects, so you learn by doing. and you will get practitioner level skills if you finish the micro degrees. And we have live classes, and in fact, that's one of the things that we are focusing on. It's not an impersonal teaching; it's very much a personal teaching and live classes, and 24/7 live labs, and of course, as I said, computer on the cloud, and personalized machines, labs and all that. And there will be real humans, real life projects, and mostly we are governed by the foundation, or the Emerging Tech Foundation. So there is a lot of industry orientation because our advisory board monitors us. And as we say, this is a job-focused, economy-creating organization. We are socially responsible commerce. So we have job-focused content. And also we are introducing some people skills where people should know how to behave in groups, in projects, and also be confident and talking to people, etc. So we are also introducing career prep support. How do I prepare for my career? Where do I go? What do I learn next? And all that stuff. People have a lot of confusion right now, but that we want to address. Okay. And also, as I said, we can bundle them into micro degrees so that you get real practitioner skills. And the biggest thing that we want to do is that we want to actually have an internship where we can give people education and also a project. And a project with a real life example, and real company that can come up in addition with the University of Emerging Tech and the foundation. And I'm very, very glad, and thanks Venkat representing CSI here. And we are actually going to announce the internships in association with the Computer Society of India and Global Engineering Deans Council, and of course, along with the Emerging Tech Foundation. So there are lots of opportunities there: the cybersecurity, machine learning with Python, and mobile app development, cloud computing, and even digital marketing for that reason. So we are into creating more jobs, more job-oriented courses. And so, for example, we have a full stack Java development, and we have an SAP ABAP program, and we have also oil and natural gas focused, data analytics and oil and natural gas and industrial automation, IIoT, the Industry 4.0, and what Bill was saying just now, the RPA, robotic process automation with the chatbots and all that stuff, and then also the introduction to Hyperledger in protecting the counterfeiting, etc., cybersecurity, all that stuff, all the jazz that you need, we are offering. And please reach out to us, and we can also customize courses for some schools and colleges, whatever you need. And the idea is to give an effective education and a practicable one, and role-based learning and experiential learning. That's the whole idea. And this is what I'm talking about. This is a virtual real-time share board that, infinite canvas, infinite boards, real-time, and you can draw anything, you can paste, you can cut and paste. You can also annotate the audio at random times and all that stuff. So it is going live. We have collaborated with this company, and this is a huge help for the students to learn effectively. So also what we do is we have certification from a nonprofit called the Emerging Tech Foundation. We can also certify people in emerging tech and all other technology related fields. So definitely we wanted to help people get a certification, and it's all about economic value creation. That's what the deal is. Again, because the shortage of time, I don't want to take a lot of time of yours, but I really thank everybody for attending this conference, and it's a huge help if you can reach out to us and ask more questions. We'd be there. But thank you again. Here is my contact for anybody to contact me.
Thank you, sir. Now, on behalf of University of Emerging Technologies and our key sponsors, I would like to thank all our speakers and attendees for making this summit happen. Without your support, this wouldn't have been possible. Tomorrow morning at 10 a.m. Indian Standard Time, we have Mr. Shahid Andani presenting his views on challenges in cybersecurity. Please visit our website for more information. That's it from my side today. Hoping to see you all tomorrow. Thank you. Have a great day ahead.
Thank you. Thank you all. Appreciate it.